the big idea that we're looking at here is that there's two different ways to layer the Earth. The first thing that happened, kind of the most obvious way to look at it, is to look at the Earth and say, well, let's break it up into the different materials. Let's figure out the different stuff that the Earth is made up of and name each layer based on that. So the first way to do it breaks the Earth up into layers depending on what materials it's made out of. And if we do that, that's this first one here. What's the first layer coming from the outside? What do you call this first layer, Bella?
The first layer is the crust.
Yeah, it's the crust. And just approximately, how thick is the crust? Oops, that should be there. But how thick is the crust? Is it? Should it go halfway in, a quarter of the way in?
Like 0.2, can you say?
The crust is about as thick as that line right there. Right? The crust is really, really super thin. Think of it as like the skin on an apple. It's not even an orange. It's the skin on an apple. So the crust is really thinner than you can draw it almost. But that's the very outer layer. Crust. There we go. So I'm going to color code it this way so it doesn't get quite as messy. So the crust is red. Whatever is the crust is made up of basically rocks like we find on the surface, made up of granite, mostly sedimentary type of rocks. That's what we're looking for. So these are rocks. The next layer, after you go in deeper than the crust, what do you have, Kai? Good. The mantle is the next one. I'll do it in green. And Kai, about how deep down does the mantle go? Should it go, a quarter of the way, halfway, 3/4 of the way? Okay. Quarter, maybe a little deeper. I like more like half. So I'm not going to quiz you guys on specific numbers, but you should know that the mantle goes about halfway down. So all this stuff right here, this is mantle. And what's the mantle made out of? If the top is made up of rocks like granite and stuff that we find on the surface, what's the mantle made up of? It's basically magma. Yeah, it's silica is the name of the type of rock. It's a type of rock. It's mostly melted, although not completely. And it's different from the rock that we find on the surface. Right? It's more similar to lava, I guess you'd say. Okay, cool. Thanks. So that's that. And then the next layer is the core. And obviously, the core is the rest of it, right? The core is approximately the inner half of the Earth. And what's the core made out of, Mark? Do you know? Metals. Good. Mostly iron. Iron's the most important one. Nickel is in there. Nickel's pretty important. There's lots of other stuff, too. That's where most of the heat that's generated inside the Earth comes from, most of it. So, crust, mantle, core. Right? If you just look at what the Earth is made out of, those are the three layers. There's really only three different things that it's made out of. So why do we have to have this second bullet here? Why do we have to have a totally separate way of naming it? Yeah. Yeah, basically. Because this is not enough to explain what we actually see when we study the inside of the Earth. Remember, most of it comes from studying earthquakes and how the earthquake waves, the P waves and the S waves travel funny through there, right? You want to sit up, please, Emily? All right. You remember the P waves and the S waves? All right, cool. So the way that they bend and refract and those shadow zones, the things that we see, they aren't explained by this. The fact that it just goes sedimentary rock, igneous rock, and then metal, that doesn't do it. What we actually see is that it goes solid, liquid, solid, liquid, solid. And so that's why we come up with a second set of names. So the first layer, if you look from the outside, and now we're doing number 2 here, what's the first layer that you see there, Andrew? Yeah, lithosphere. Litho means rock. And how thick is the lithosphere compared to the crust? It's a little bit thicker. Good. You need to know that. That's actually important. The lithosphere is actually made up of 2 different materials. It's made up of a little bit of crust, and it's not that thick. I drew it too thick. but it is thicker than the crust. Right? The lithosphere is made up of the crust and the upper part of the mantle. The mantle, basically the part of the mantle that is not hot enough to melt yet. The important thing about the lithosphere is that it's solid. If you go down deeper under the earth, remember the heat and the pressure, the heat starts to build and build and build. Pretty soon, at the bottom of the lithosphere, it gets hot enough to melt the rock. And what do you call it once the rock is hot enough to melt, Savannah? Yeah. Good. It's a tough one to say. It's the asthenosphere, though. This guy right here. All right, so next comes the asthenosphere, and approximately how much of the mantle is made up of asthenosphere? Is it about half or a quarter or a third or... Do you know? You don't know? It's not very much. It's about a quarter of it. So that right there is the asthenosphere. But it's really, really important because remember, and actually this is what we're going to talk about today. This is today's new stuff. The exciting thing is that in the asthenosphere, you get those convection currents. And that's what gives their surface all of its characteristics. So you've got a liquid asthenosphere. All right, good. Hey. Okay, we got him too. Yeah. All right. Wait a minute. I read the name wrong. We don't have him. Hey, I'm sorry about that. We don't have this fella. Did you guys miss me? I missed you guys. All right, good. Below the asthenosphere, it stops being liquid, which is really weird, right? As you go down deeper and deeper, you would expect it to not. You'd expect it to get hotter and hotter, and things are just going to get more and more liquidy. The problem is there's so much pressure that it squeezes stuff together. All right, so the pressure is enough that it starts to hold the rocks back together in a solid. What do you call this layer where the rock becomes solid again? What do you say, Carrie?
Oh, what? The mesosphere.
Okay, thank you. The mesosphere.
Yeah.
That's where, yes, it's still hot. It's hot enough to melt rock, but the pressure is so intense, it squeezes it so hard that it can't act like a liquid. All right? And then you get to the last two, and the last two we don't need to talk a ton about, I don't think, because everybody knows where the core is. And it's not hard to figure out which one comes first, the inner core or the outer core either, right? But what you do need to know is that it goes liquid-solid again for the same reason. There's an insane amount of heat at the center of the Earth. So the outer core is liquid. Because there's so much heat. As you go down deeper, it's not like it cools off any. It doesn't. In fact, it gets hotter. Right? But there's so much pressure that the rock of the inner core is squeezed together so much that it actually cannot be a liquid, so it's a solid. All right. So there's that. Any questions about that? Did you guys complete this? Did you get all four of those things filled out okay? We basically talked about the last two as we went, so I'm not going to talk about them directly unless you have questions. But that's what you need to know about the interior of the Earth, what it's made out of. Now that we know about the interior of the Earth, can I just be honest with you guys? We're friends. We can trust each other. I can be honest with you, right? I mean, we're friends. We can talk. The surface of the Earth is really what we care about. I'll be honest about that. The reason we had to know what's going on inside the Earth is because it explains things that we actually see on the surface. Right? So we see convection currents caused inside the outer core because it gets heated up at the bottom and the liquid metal flows to the top and then it flows back down. These convection currents, the moving liquid, basically allows for the Earth's magnetic field. Right? That magnetic field is super important because without it there would be no life on Earth, at least not like we recognize it. The sun would give off it does give off high energy particles, but they would kill us all. And then probably even more important, or at least more obvious than that, the convection currents up here in the asthenosphere give us some really important things that we see on the surface of the Earth. And that's what we're going to talk about today. So, flip through the other side of your spiral. We've got notes. I'll be honest with you. It's a lot of notes. It is. In fact, when I got this slideshow from another person, it was 48 slides. You like that? 48 slides? And I said, no, 48 slides is too much. So I went through and I got rid of as many as I could, and I was able to get it down to 32 slides. That's still too much. So we're going to take those 32 slides, cut it in half, and we're going to do it in 2 days. So, you're welcome. As horrible as you think this slideshow may be, it used to be 4 times more horrible. So, maybe you can take some comfort in that. And if you can't, then, we got it online. You can press pause and go get it over. All right. So what we're studying today is the crust. Right? And really, that's what we care about because we live on the crust of the Earth. Just the very outer, I don't know, it could be as much as 15 miles or so, 25, 30 kilometers. Usually the crust is no thicker than that. We're studying the crust. Right? It turns out that the crust, and this is the idea of plate tectonics, the crust is broken up into pieces, and those pieces move around. That's going to be really important. But before we get there, you do need to know this. This is important. There's 2 different types of crust. And they behave, they look, they act quite a bit differently. The first one is continental crust, which makes up the continents. The 7 major continents from geography. And then there's also oceanic crust, which makes up the ocean. So you can get it from the name. But there's a big difference between them. The continental crust is usually a lot thicker. How thick? Not that thick still. In the neighborhood of maybe 10 to 25 kilometers. So what is that? That's like 6 to 18 miles or thereabouts. Not very thick compared to the size of the Earth. Not very thick at all. But thick compared to the oceanic crust. All right, it's thick, so that's this stuff. This is the continental crust on the left side. In this picture, it's on the right side. But it's the thicker stuff. And it's lighter, too. It's less dense, which means that it floats up above. That's why the continents stick up and the oceans don't. Right? The oceanic crust is down low, and the water flows over it and fills it up. So continental crust, think of it kind of like styrofoam, right? When you put styrofoam on water, it floats up out of the water a lot, right? Well, the continental crust, when you put it on top of the mantle, this is the mantle down here, it floats up because it's less dense, right? Just like the styrofoam floats up. The oceanic crust is thinner, but it's also more dense, so it tends to sink down, and since it's lower, the water pools up on top, and that's why you have oceans. So that's the big idea. The oceanic crust, if I'm going to give you a comparison, is somewhere in the neighborhood of 5 to 10 kilometers. So what is that, 3 to 6 miles? When you're talking about the whole size of the Earth, that's tiny. And then both of these types of crust float around on the mantle. Would it shock you to hear that those pieces of crust actually float around, they move? Have you heard that before? Yeah, it's crazy business, but it's actually true. The Earth's crust is broken up into a bunch of different pieces. There's more or less 7 different plates, close to 1 for each continent. Not quite, because Europe and Asia are the same continent, and then we have a huge Pacific plate, which is underneath the entire Pacific Ocean, or most of the Pacific Ocean. But it's close to 1 plate for each continent. So if someone asks you which continental plate do you live on, could you answer that? Take a look at the map. Yeah, it's not complicated. We live in North America, so we live on right about here, right? The North American plate. Well, we'll talk about this later on. It's actually it's one of those doomsday scenarios. There's a plate right here. It's one of the smaller plates. It doesn't show up on this map. It's called the Juan de Fuca plate. It's fun to say. Say Juan de Fuca.
Juan de Fuca.
All right, everybody stop and listen to Gage. That's how you should say Juan de Fuca. Go.
No, I do it, brother.
Come on, man.
No.
There's no shame in it.
No, I don't want this.
You be proud of who you are.
No.
All right, fine. It was good. It was good. I hope you had the. What? No, it wasn't. I'm telling you, don't have shame. That was a strong word. All right. So anyway, the important idea is that these plates are constantly in motion, and the reason why we care about that is because the motion of these plates explains earthquakes and volcanoes and mountains and valleys. It explains so many different things that we see. So if we're going to be scientists and try and understand the Earth, we need to know that these things move around. All right, hey Juan, stop. The first thing that I want to do is I want to convince you that the plates really do move around. So I'm going to present to you guys 5 pieces of evidence. 5 arguments for the plates actually moving around. And honestly, they get increasingly complicated, but also increasingly convincing too. So the first couple won't be too bad. And let's start with this idea. Do you know that you've heard of the idea of Pangea?
Yeah.
Right. We have pretty good reason to think, and good evidence to think, that 225 million years ago, all of the continents of the Earth were pushed together. So there was basically one giant landmass, one supercontinent, it's called, and the rest of the Earth was covered in ocean. Right? And to give you a little perspective, 225 million years ago, is that a long time compared to the age of the Earth? When you talk about the age of the Earth is about 4,600 million years. Right? So compared to the age of the Earth, that's not old at all. Right? In fact, if the Earth, just to put it on scale, if you were talking about the age of the Earth as one day, Pangea would have been an hour ago. Right? If the Earth were one day old, 24 hours, Pangea would have been a little over an hour ago. So actually, in terms of the age of the Earth, not very long ago. We think there have been several supercontinents, that it's all been pushed together and broken apart and pushed together and broken apart. Pangea is the most recent. The other thing to realize is that there were no dinosaurs at Pangea. Right? So when we think about the age of the Earth, dinosaurs showed up somewhere in that neighborhood and went extinct somewhere in this neighborhood.
Maybe they didn't go extinct and they went on an island, a tiny one, and then it fell into the ocean and they all died.
But maybe that island didn't fall into the ocean and we can go live there and have pet dinosaurs.
Or they
I like that.
Or they went to the future.
Okay, 5 pieces of evidence for plate tectonics. The first one is pretty simple, and I know you've seen this before. I call it the lock and key piece of evidence. It's not all that convincing. You just look at it and it kind of looks like there's places, if you look at a map, there's places where the continents would fit together. Right? When you look at South America and Africa, that's the best example. Go back to the picture of Pangea, and you can see we think that South America and Africa were actually nestled together like that. We also think that North America was nestled in there. So this is Florida, and this is the east coast of the United States. It used to be nestled up against kind of the northwest corner of Africa. There's certain places where you can look at a map, and this one's more obvious. Sometimes it takes more creativity, but you can see it looks like they fit together. Doesn't mean that they did. It's just kind of, it might get you wondering, right? Kind of looks right. So if we're gonna believe it, if we're really gonna believe it, we need better evidence than that. So evidence number 2, fossil records make us really start to suspect that the continents have to move around. And what I mean by that, there's a couple different things that we see. Number 1, you might see that there's a species, like this one right here, that can't swim. Yet that species that can't swim shows up in South America and Africa. Right? How does that make sense? I mean, is it like a Life of Pi thing where they float across on a raft and they just end up there?
Yeah.
I doubt it. Or is it more likely that they actually were pushed together? I don't know. It could be either one, honestly. But here's one that doesn't make any sense without the continents moving around. We also find, if you look at Antarctica, you guys know about Antarctica, right? Cold there?
Yeah.
When you look at Antarctica, there's actually fossils that are tropical. Tropical flowers, for example, that we find fossil records in Antarctica. Right? So that doesn't make any sense at all, unless Antarctica hasn't always been there.
Maybe it was Hawaii.
Unless it was pushed around, it used to be someplace warmer. So fossil evidence is evidence number 2. And when we look at the fossils of animals, it starts to make us think maybe there's something to it. It's almost the same thing, but it's a little bit more convincing because rocks cannot go Life of Pi. Right? What do I mean by that? I mean that rocks can't cross the ocean. Right? At least not by their choice. So when we look at the composition of the rocks, and did you guys know this? If you gave a geologist, someone who studies rocks, a rock that you picked up out in the forest, and you took it to them, they could go to their lab, and they could almost 100% tell you where that rock came from. They can say, oh, that came from Southern Oregon, and that rock was made in, that rock is 100 million years old, it came from such and such. There's fingerprints left behind. If you look at the minerals, if you look at the magnetic tracers, you can tell where a rock came from. Well, when we do this, when we look at where the rocks came from on opposite sides of the ocean, sometimes they came from the exact same spot. So here's a good example. If you look across the Atlantic Ocean and you push things back together, you find the exact same rocks, say, in the Appalachian Mountains, the eastern United States, as you find over here in Western Europe, Scotland, for example. That starts to look a little suspicious. Like, okay, maybe those rocks formed together, and then the continents moved apart. Next! So, number 1, the lock and key, the fact that the continents fit together like a puzzle. Number 2, fossil records. Number 3, did I skip one? I must have skipped one. Number 3 is the rock records. What the heck? No, I'm missing one. What about 4 and 5? I'm not gonna cheat, guys. I'm giving you 4 and 5. You're better than that.
Can you go back to the 1 and 2?
1 was the lock and key.
I mean 2.
Age of sea lure. I cannot go back to 1 and 2, but you are more than welcome to. They have this thing called the interwebs that you can look on, and all this stuff will be there. All right. Hey, if nothing else, it's a pretty picture. Zoom in, you monkey. There we go. All right. Here we go. This is the picture. It's a little bit confusing to look at, but what you're looking at, these colored parts, are the ocean floor, right? The oceanic crust of the Earth. And what we can do is we can send ships down, submarines down, and they pick up a piece of the crust. And we take it and we do radiometric dating and figure out how old that crust is. It turns out when we look at the age of the seafloor, the seafloor is youngest in the middle. Right? Another interesting thing is when we look at the seafloor, this is the Atlantic Ocean right here, right? This is the United States. Here's Africa and Europe, the Atlantic Ocean in the middle. When we go down to the bottom of the Atlantic Ocean, pretty much right smack dab in the middle of it, and it runs all the way pretty much from North Pole to South Pole, there's this ridge where you've got all kinds of volcanic activity, right? Magma bubbling up from underneath the Earth and forming new seafloor. Well, gets you kind of thinking, well, maybe there's new floor forming in the middle as these continents move apart, right? Whoa. Am I freaking you out yet? Is there any evidence behind that? Yes, there is. It's not just looking at it and thinking, hey, that could happen. When we go down and we do radiometric dating, what we find out is that when you look close to the ridge, these rocks are all new. And as you go up and down the Atlantic Ridge, they're basically the same age close to the ridge. As you go a little bit further away, notice what the colors mean, right? As it goes towards the blue and purple end of the spectrum, the rocks get older. So the further you get away from the ridge, the older the rock is. That means that this rock was laid down, what does it say, about 60 million years ago. Well, what we think is 60 million years ago, these were together, and there was new rock forming in the middle, right where my pinkies are. Right? And then they moved apart, and they got older, and new, younger rock was formed in the middle. Matches up perfectly, and that's what we see. The oldest rock, if you look here, the blue and the purple, is always right up against the edge. The youngest rock is always right at the ridge. And it matches up perfectly. So that was evidence number 4, the age of the seafloor. Yes?
Why is there that huge blue spot on the right?
Why?
Yeah, well, why is it so?
Why are you so old, Pacific Ocean?
Because it's showing the others, it goes around.
Right, this is the Pacific Ocean. This is the Pacific Ocean, right?
Yes, I know.
And the Pacific Ocean, it turns out the Pacific Plate is actually doing the opposite of what we see here. These are pulling apart from each other, right? We call that a divergent boundary. The Pacific Plate is actually going like this. It's being pushed underneath the Asiatic Plate. So this is the oldest stuff right here, and there's younger, although not really young stuff on the other side of the Pacific. All right. Hey, play nice, kids. Evidence number 5. Last one, and it's a little bit confusing, and I'm going to give you the abbreviated version of it, but it has to do with the magnets in the rocks. Right? You know that if you take a magnet, take a magneto, I had one. Here's a magnet. You take a magnet and you hold it against something that's metallic. What's something metallic? Here we go. Ooh, I got a better idea. Don't you love it when I get ideas? Take a magnet and you let something metallic come near the magnet. All right, then what happens is that metallic stuff always lines up with the magnetic field. Right? It just does. If you take this is just basically steel powder. But when you sprinkle it on there, it always lines up with the magnetic field. It does that automatically. Well, the Earth has a magnetic field. Do you guys know that? Yeah, if you use a compass, you know it easily. Basically, inside the Earth, there's a giant magnet. The North Pole of the magnet's actually at the South Pole, and the South Pole's at the North Pole. Don't worry about that. But inside the Earth, there's a giant magnet, and so the magnetic field lines basically always run from north to... wait a minute. Yeah. Magnetic field lines of the Earth always run like this, basically from north to south. So what that means is that if there's anything magnetic at all in rocks, and there is, right? There's metals in the rocks here. Inside those rocks, the metals are going to line up with the Earth's magnetic field. They have to. That's what metallic stuff does around magnets, right? Oh, look at this guy. It's curling over. Okay. How far can you go? When we look at the rocks, we don't actually see that they are lined up with the magnetic field. How is that possible? Well, if you look, for example, you could look at the continent of, you guys test my art skills. What continent is this here? Could be South America. I was going for Africa. No, it's not a nose, or an ear, or a potato. It's Africa. The continent of Africa, you could, for example, see, you would expect, if the continent of Africa always is where it has been, or is where it always has been, you would expect that as the continental crust was laid down, it would have been liquid, at which point the molecules could line up however they wanted. When it cooled, it solidified, when it froze, basically, then the magnetic field would always be pointed this way in the rocks, right? That's not always what we find. Sometimes we go up to a continent, and we see that the magnetic field lines look like that. That don't make no sense. Unless Africa used to be whoop, like this. Right? Unless Africa used to be twisted and then it drifted into this position. There's also some complicated stuff with the Earth's magnetic field flip-flopping in directions. More than I want to get into right now. But we can definitely say that it all adds up. All right? So 5 pieces of evidence. What are the 5 pieces of evidence for plate tectonics? What's one of them, Brian?
Like the fossils.
All right, the fossil records. Good. What's another piece of evidence, Kaylee?
The age of the rocks.
Okay, the fossils. We got the rocks. Are you talking about the age of the seafloor? Okay. Fossils, age of the seafloor. I like it. What's another one, Laura? Puzzle fits. We got 2 more. What are they? Give me one, Kendall.
I said like what they already said. I didn't get it.
Well, check your notes.
I got Lock and Key, Animal Fossils, Rocks, and then Age of Rocks.
Okay. What do you mean by rocks? Maybe look at the board. That might help.
Just like how they moved. Oh,
No, that doesn't really cut it. What does this picture show you?
that they're same rocks on different sides.
Okay, good. You have the same rocks on different sides of the ocean. I'll take that. We got one more. Who knows it? You got it, Laura? Yeah, good. If we look at the way the magnetic field lines up in the rocks, it definitely suggests the continents are moving. Know those 5, guys. Make sure you get them in your notes. That way you can get them in your brain. All right. So those plates are moving. Now let's look at why they move. That's the next thing. I got to convince you of why these plates are moving. Why, oh why do you move? Convection is the answer. Right? And I'll be quick about this because we talked about it a little bit last time. But basically, if you look at the Earth, you could think of the Earth as a giant pot of macaroni and cheese. And I like to do that because I love me some eating. There we go. Right, there's your big old pot of macaroni and cheese. And when you get that macaroni and cheese heated up, it starts to bubble and churn, right? And you notice the noodles, they're kind of floating around on the surface. Because when you put it on the stove, there's this heat source at the bottom. Where does the heat source come from inside the Earth? Yeah, it's in the core, right? It's, if you look at just the asthenosphere, this is the asthenosphere here, the liquid part, the heat source comes from beneath it. So what happens is the asthenosphere gets heated up at the bottom, and you get these convection currents. We talked about this last time. Heats up at the bottom, whoop, goes up towards the top. And once it's at the top, it has to go somewhere, so it curls back around to the bottom. This guy goes, and this guy goes. And what ends up happening is just like the noodle. If a noodle floats to the top, it doesn't just sit there. It gets pushed around on the surface. The crust floats around on the surface of the Earth too, because these currents are moving underneath it. It's almost like a raft sitting on the river. When the river moves, the raft moves with it. So the continents end up moving. Do they move fast? No, real fast. You know, we're talking in the neighborhood of a couple inches a year usually. A foot a year maybe, if they're moving real fast. But over millions of years, it adds up. All right. We're going to stop here. Right now, you need to basically just know this stuff. All right, do this. Give yourself a little pop quiz right now. See if you can answer these questions.